Okay, so for the last part of this project, we're going to talk about Fermat's Little Theorem. And Fermat's Little Theorem is something we've mentioned before. Do you happen to remember what it is? It's probably been 2 years since we talked about it, though.
No.
Does it ring a bell? It says a number a, an integer, to the p minus 1 is congruent to 1 mod p. So let's take a look. What do I mean by this? Let's say that our prime, usually when we're talking about integers and we use a p, we mean prime. Let's just say our prime is 7. And let's look at what is 1 to the 6th.
Which is, that's 1.
1, is that 1 mod 7?
Yep.
Alright, how about 2 to the 6th?
64.
When 7 times 9 is 63.
So, 1.
Yep, equals 1 mod 7, or congruent to 1 mod 7. How about 3 to the 6th? What would we do there?
Well, we could do 3 cubed and then square that.
And sometimes. So,
Because I guess we're getting kind of large, so we need a method to do for larger numbers.
Okay, so 3 cubed is
27.
27.
So that'd be 720.
Well,
Just
mod 7. Yeah, mod 7 were
3.
6.
6.
6 mod 7.
6. And then what do we have to do with 6?
Then we have to square that. 36, which is 1 mod 7.
So another thing you could have said is that this was congruent to minus 1 mod 7. There. Okay, so that seems to be true for 3, but 4 to the 6th.
So 4 cubed, that's 64.
Alright,
Which we know is 1.
And then 1 squared, that's just 1.
good. Good. We knew 4 cubed was. Alright, 5?
And 5, I guess we can square 5 and then cube our result.
Okay, square 5 and then cube the result, so that's 25, which is congruent to
4, 1, 7.
1, 7.
Cubed
4
is,
cubed is 64,
which that was 1.
1. Okay, so it's working, and so we just got to check 6 now. 6 to the 6th. Can you think of a clever way to check 6 to the 6th mod 7?
Well, 6 is minus 1 mod 7.
Oh, okay, that's one way. Yeah, that wasn't even what I was thinking. Minus 1 to the 6th.
Minus
Mod 7.
1, so that's going to be 1.
Okay, good. Any other way you could think to check 6 to the 6th mod 7? It's different from how we've done before.
Six to the 6th. That's a completely different way.
Yeah.
Well,
so-
you could do 2 to the 6th and 3 to the 6th.
Yeah.
Because we know both of those work.
Yeah, 2 to the 6th times 3 to the 6th, which we already knew were both 1. Okay, so Fermat's Little Theorem says that this is true for any prime and any integer, any prime.
Alright.
Alright.
So that plays a role in this thing. But this is a neat theorem. Are you familiar with any other theorems affiliated with Fermat?
I know the name is of them. Like this Fermat's last theorem.
Do you know what that said?
No. I mean, I probably do, but I don't remember it with the name.
Have you heard of Fermat's last theorem?
I have, but I just don't remember what it is.
That says a to the n plus b to the n equals c to the n only has integer solutions for n equals 2. Well, sorry, actually that's not what it says. That there are no solutions greater than n equals 2. Obviously there's lots of solutions for n equals 1.
Yeah.
And this was actually, this was famously conjectured by Fermat. But it was only proved in, I guess it was 1994 by a Princeton, sorry, by a mathematician at Princeton named Andrew Wiles, with a little help from a mathematician from the UK named Richard Taylor. But no solution. So there's, so like for for n equals 2, we have 3 squared plus 4 squared is 5 squared, the famous example. But there are no cubes. There are no cubes at all that satisfy. You know, whatever, like 10 cubed plus 11 cubed is not 12 cubed or something like that. No solutions at all. It's pretty amazing. So yeah, so this simple idea in number theory, that if you take any prime and any integer to the prime minus 1 power, you always get 1 mod that prime. That is a key fact for why, this simple fact is a key fact for why when we take primes and 1 over them, if we have an even period, we can take the first and last bit of the period, add them together, and get all 9s. Doesn't seem like these would be related at all, right?
Yeah.
No.
So that's pretty cool.
Yeah.
Alright, so what do you think of this?
Interesting.
Pretty neat.
It's pretty interesting.
Pretty neat. Pretty neat fact about primes that we learned today. Okay, hey, good job guys.